Hi, my name is Alec Tubbs, and this is my Lab4 report. The purpose of Lab4 was to gain a better understanding of circuits by creating various circuits using an online software and seeing how these various circuits behaved. Results that were calculated computationally using knowledge gained in class were compared to experimental results that were gotten from the online circuit making software. In the first part of the lab, I calculated a current of 0.204 amps, which agreed with the results that I got from the program. In the second part of the lab, I found that increasing the resistance of a resistor from 10 ohms to 20 ohms seemed to double the time that it took for a capacitor to charge and double the time that it took for the capacitor to discharge. In the last part of the lab, the RC part of the lab, I calculated RC to be 5.98, which is very similar to the expected value of 6. The main physics concepts at play for this lab were the loop rule, which states that the voltage drop around an entire loop of a circuit is 0, the node rule, which states essentially that current is conserved, the idea of resistors, which are elements of circuits used to regulate current, and the idea of Ohm's law, which states that resistance is equal to V over I, capacitors, which are essentially mini batteries that build up and store charge, where capacitance is equal to charge over delta V, and the idea of RC circuits, which are simple circuits that have both resistors and capacitors. Now I'll go through some of my data and observations. For the first part of the lab, we were dealing primarily with a circuit that had two resistors connected in series. Based on their values for their resistances, I calculated the current through the circuit to be 0.204 amps. This agrees with the results that I got from the simulator program. However, when I changed the connections, the signs in the program didn't change, which was slightly confusing to me. Next, we disconnected part of the circuit and used a voltmeter to calculate the potential drop between the gap that was now there. The voltmeter read 3 volts, which makes sense because the total voltage given to the circuit by the batteries is 3 volts, and the ammeter now read 0 amps because the circuit is not connected, so there's no current flowing. Parts 5 through 8 of the lab asked me to calculate the voltage drop over various different segments of the circuit, and before doing so, predict what the total voltage drop should be over the entire circuit. I predicted that the sum of all the potential differences should be 0, and this is the result that I got, which you can see with my work to the right. After this, I made a graph showing the voltage as you go through the circuit. So between each of the batteries, it jumps up to 3. Then after you go through the first resistor, it goes down a little bit. And then after the second resistor, the voltage is down to 0. The next part of the lab asked me to place an ammeter in parallel with one of the resistors and see what the current through the circuit would be. The current through the circuit was now 0.06 amps, which makes sense because of the node rule, meaning that current must be conserved. The next part of the lab involved modeling a simple RC circuit, first with a 10 ohm resistor, then with a 20 ohm resistor. With the 10 ohm resistor, the light went out after 5.7 seconds, which means that the capacitor was essentially charged after 5.7 seconds, while the capacitor was discharged after 9.5 seconds. With the 20 ohm resistor, the light went out after 9.51 seconds. Meanwhile, the capacitor was discharged after 18.33 seconds. With these results, I noticed the fact that doubling the resistance seems to double the time that it takes for the capacitor to charge or discharge. The last part of the lab dealt with trying to experimentally determine a value for the quantity RC, which is resistance times capacitance. To do this, I charged a capacitor to its full charge of 9 volts and then calculated the voltage difference at different time intervals while letting it discharge. Taking the natural log of the 9 volts over V naught, which is the voltages that I calculated at the different timestamps, and plotting that versus time, I was able to calculate an RC value based off of the slope of the graph of 5.98, which is very similar to the expected results of 6. To conclude, I'll answer a few questions. First, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? Well, in real life, actual ammeters do have a small amount of resistance associated with them. So this means that the results that we got in this lab are slightly smaller than the results we would get in real life. Secondly, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, real capacitors also have a small amount of internal resistance, so the capacitor would take slightly longer to charge.